Welcome students. We want to discuss the concept of continued fraction. So note that this set of notes is a very small minor teaser to the theory of continued fractions. For proper treatment, you should read the textbook, and for a better treatment, you should read some books. For example, there is a continued fraction book by C.D. Olds. Okay. It's published by Cambridge, although the book is discontinued, but you can find it online. Now, first of all, what is a simple continued fraction? So a simple continued fraction is an expression of form a0 plus 1 upon a1 plus 1 upon a2 plus dot dot dot. Keep on going like that. It can stop at finite step or it can keep on going. Here, a0 has to be an integer, any integer, positive or negative or 0, and a1, a2, a3, so on are positive integers. Okay. Note that there are other expressions. So here it seems like it's only defined where a0 and a1, a2, an are positive integers, but you can have a similar extension in any commutative ring. But we'll leave that for your future investigations. Now, this expression looks tedious, so we'll write this expression in short for as a0, the first one, with a semicolon, a1, a2, dot, dot, dot. Now, if this terminates at some step, then we call it as finite simple continued fraction. So what does it mean? It means that you have a naught plus 1 upon a1 plus 1 upon a2 plus 1 upon blah, blah, blah. It stops at an. Then we call this as a finite, the name finite for the obvious finiteness, continued fraction. Now note that these a0, a1, a2, an are called partial quotients of the continued fraction. And we use the short notation again for the finite one is a0 semicolon a1 comma a2 comma a3 comma dot 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 an. Now let's do one computation of a finite continued fraction. So the finite continued fraction for rational numbers has a strong connection with the Euclidean algorithm. So let's see. So we have 415 divided by 93. So 415 or 93, you use Euclidean algorithm. So you'll go 415 is 4 times 93 plus 43. Then you divide 93 by 43. You get basically 7. Then you take 43, you divide by 7, you get 6 times plus 1. And then you get what? 7 is 7 times 1. So now if I want to write a finite continued fraction of this is going to be 415 divided by 93 is going to be, take this guy and divide both sides by 93. So 415 by 93 is going to be 4 plus 43 by 93. So that is step 1. And now I can write this as 4 plus 1 upon what? 1 upon 93 by 43. Right? And I'll use this part now. So from here, what do I get? I get 93 by 43 is equal to 2 plus 7 by 43. So I can write this as 4 plus 1 upon, instead of 93 by 43, I'm going to write 2 plus 7 by 43. So which is demonstrated here, 2 plus 7 by 43. There should have been 43 here missing. Now I can write this as 2 plus 43 by 7, right? So 2 plus 1 upon 43 by 7. Now what is 43 by 7? So let's write 43 divided by 7 is going to be 6 plus 1 by 7. So then I write it as 6 plus 1 by 7, and that's where it stops. So my expression for the continued fraction is going to be 4 semicolon 2 6 7. Now note that this has also connection with the coefficients of here. You see, you're writing 4 comma, then next one is 2 comma 6 comma 7. So from Euclidean algorithm you can read off the continued fraction. So now, so this is how you compute a continued fraction for a rational number, right? So there are few results about it. So seems like for a rational number, at least in this case, which is 415 divided by 93, it's a rational number. For this rational number, I can write it as a finite continued fraction. All right. Now, so seems like every simple continued fraction represents a rational number. And so this rational number can be represented by a finite simple continued fraction. And consequently, we can show that every finite simple continued fraction represents a rational number. So how do we go about it? So let's embark on that, proving that theorem. So we'll prove it here. So proof. So question 1, every rational number has a finite continued fraction representation. Finite simple continued fraction representation. So we'll start with the following. So let x be a rational number. So a rational number of form a by b, where b is not 0. Without loss of generality, take b greater than 0. Well, we can take the negative sign in a. Now recall the extended Euclidean algorithm. So in extended Euclidean algorithm, you had R0 was a and R1 was b, and then the Euclidean algorithm produced the following string. So we have R0 equals to R1 Q1 plus R2. Your R2 is between R1 and greater than 0. Then you have R1 equals to R2 Q2 plus R3. And you keep on going until you get Rn minus 2 equals to Rn minus 1 times Qn minus 1 plus Rn, and your Rn minus 1 is Rn Qn. And what are these relations? So you have your R2 is going to be less than, sorry, so here you have R2 less than R1. So here you'll have R3 less than R2 greater than 0, and so on. And until here, you will get 0 less than Rn minus 1 less than Rn minus 2, and then it stops here. Yeah. So note that in all these things, in all these expressions, your Q1, Q2, Q3, Qn, these are what? These are, so Qi's are positive integers, right? All the way starting from where? From all the way from where? From Q2 onwards. So I going from greater than equal to 2 less than equal to n, right? So now in this case, we can write, so let's write down, so our A by B is going to be, so A is R0, right? So it's gonna be R0 divided by R1, right? Because your R1 is B, recall here. So that is going to be, now I can write this as R0 divide. So if I divide this equation, divide by R1, what do I get? I get Q1 plus R2 divided by R1. Yeah. And now I can, since I want 1 here, I can write it as R1 divided by R2. Okay, now basically this is going to be Q1 plus 1 upon, now R1 divided by R2. So if I divide by, so I divided here by R1, I'll divide by, so let me make a distinction here. So divide by R2. So this will give me R1 by R2 is Q2. So R1 by R2 is Q2 plus R2 by R3. Now you keep on doing this until you reach, basically, you will keep on doing this until you reach Q1 plus 1 by Q2 plus 1 by Q3 plus 1 by Q4, all the way dot dot dot, all the way it goes until 1 plus 1 by Q1. So therefore, in this case, the expansion or the continued fraction expression for this is going to be simply starting with what? You start with Q1, and Q1 need not be positive, right? I mean, like, because if you're dividing, say, -5 by 2, right? Then if you're dividing -5 by 2, then clearly you'll have to have a -3 here plus remainder of 1, right? You can't have a positive number here, right? If you're dividing a negative by a positive number, right? Okay, so we get what? So we get Q1, Q2, dot, 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 Qn. So this is how you can find out continued fraction for a rational number. So you have shown that if you take a rational number, the continued fraction is finite. So then the question one should ask is, now we see that it's based on Euclidean algorithm. So question is, does the Euclidean algorithm terminates? Right, I mean, like, although it may look clear to you that it does, but does the Euclidean algorithm terminates? And what is the running time, right? So how many steps are required? How many steps are required? So there are various estimations of this. So the best estimation for at least the one I'm aware of, there are better estimation, is by Knuth. In 81, he showed that it's going to be, if you have A less than equal to B and you're running Euclidean, so Euclidean algorithm will take 1.9405 log A base 10. So there are better estimates. You can also, so the most basic one was given as a consequence of Lamy's theorem. You should have a look at that. Okay, so first things first. So this Euclidean, so every rational number has a finite simple continued fraction. And in some sense, the extended, the Euclidean algorithm actually gives you a way to find out it right away. Okay, here. Now, another interesting fact is, suppose you have, say, a number, say 3 by 4. Yeah, and you want to write down the so question continued fraction for 3 by 4. 3 by 4. So now 3 by 4 can be written as 0 plus 1 upon 4 by 3. So this is going to be 0 plus 1 upon 1 plus 1 by 3. And therefore, the continued fraction is going to be 0. The first term is 0. Next term is 1. And the next term is 3. Okay. So the idea is if you have fraction a by b with b or a is less than b, then we have what? We'll have the first term is going to be what? 0. And of course, these are positive, no? Because if we have negative, then clearly you don't, right? So this answers your question. The first question or the first theorem was every rational number has a finite continued simple fraction. Okay. Now let's ask the question other way around. The other way around question is question 2, or the theorem 2, if you want to call it. So theorem 2, does every finite continued fraction simple represents a rational number? And the answer is yes. So this is a theorem, so it shouldn't start with does. Every finite simple continued fraction represents a rational number. So let's start with a finite continued simple fraction. Oh, sorry, finite simple continued fraction. So we have a0, a1, dot, 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 an. So we'll prove this. So proof will be by induction. So proof by induction. On n. So when n equals to 1, we have a0, a1 is going to be a0 plus 1 by a1, which is going to be a0, a1 plus 1 divided by a1. Now note that when you have a finite, so you have a simple continued fraction, that means a0, ai belong to z, and a1 belongs to z, and your a1 is positive integer, so a1 is greater than 0. So these are integers, so this belongs to q, or is a rational number, or in other words is a rational number. Why? Because a0, a1, so this implies a0, this is not ai, this is 1, so a0, a1 plus 1 and a1 belongs to Z with a1 not equal to 0. So if you take ratios of two integers, you get an rational, right? Of course, you're dividing by a non-zero integer. Okay, so for n equals to 1, it is true. So base case is true. Now assume it true for n equals to k. This would mean what? This implies a0, ak is a rational number. Is a rational number. Now we need to prove for, so this was induction hypothesis. Now let's prove it for, now to prove for n equals to k plus 1. Now note that the way you have ak plus 1, this can be written as a0 plus 1 upon a1 all the way until ak plus 1. And this is irrational, right? This belongs to Q, right? Why? Because of the induction hypothesis. Because of induction hypothesis. And your A0 belongs to Z, right? So you add, so this implies A0 also belongs to Q. If you add two rational numbers, you get irrational numbers. Therefore, A0 AK plus 1 belongs to Q, right? That is same as saying that this is a rational number. Therefore, by mathematical induction, A0, A1, AN is rational for all, is a rational number. So you have proved that gives you a rational number. So you showed that any arbitrary finite continued fraction represents a rational number. So that is this theorem here. So both the theorems now make sense. Then the next question we should ask is that the following. So since finite continued fractions, again, we are going for simple. So since finite simple continued fraction represent rational numbers, is continued fraction for every rational number unique? And the answer is no. There are two representations. One, so the idea is you can write the last an to be an minus 1 plus 1 upon 1. So you can have basically two representation for a rational number. All right. So let's see an example of this two representation. So let me go back to the previous example. So we have here, so I had 415 divided by 93 was given by 4 plus 1 upon 2 plus 1 upon 6 plus 1 by 7. Now I can do the following. Instead of writing it as 1 upon 7, 6 plus 1 upon 7, I could have done the following. can write it as, this is going to be 4 plus 1 upon 2 plus 1 upon 6 plus 1 upon, now I can write this as 1 upon 1 upon what? 1 plus, so 1 upon 6 plus 1. In that case, I will get a continued fraction of length 1 more than the other one. You have 4, 2, 6, 6, 1. In general, if you have a0, a1, dot, 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 until an as a representation for your finite continued fraction, you can always take the last step and write it as an minus 1 comma 1. Why is that? Because an is same as an minus 1 upon 1. So in the last step, if you have 1 upon an, instead of that, you will write this part. So whatever this part is here, you will write it as 1 upon, you can write it as 1 upon an minus 1 plus 1 upon 1. And in that case, you'll get an extra 1. So this is the idea behind it. Yeah. So but beyond this two different representation, the simple continued fraction representation for a rational number is unique. Okay. So now then the next question is, we know that every rational number is represented by finite continued fraction. The next question is, how about irrational number? Can they be represented by finite continued fraction? And the answer is yes. So, but it won't be a finite continued fraction. So rational numbers are given by simple continued fractions which are not finite, because if they are finite, they represent rational numbers, right? So there is a procedure for this. So the procedure is as follows. Say alpha equals to alpha naught is a rational number. You define basically finite. You want to construct the finite, sorry, my bad, not finite. You want to construct a simple continued fraction for this, starting with a0, a1, a2, blah, blah, blah. It won't be finite. So the way you go about it is as follows. So you take, so a0 will be integer part of alpha 0. And then from there, you construct alpha 1 as 1 upon alpha 1 minus the alpha 0 minus a0. Then you go to the next step, you basically get a1, you get 1 upon alpha. A1 is integer part of alpha 1. And then what do you get? You can get alpha 2 as 1 upon alpha 1 minus a1. And you keep on repeating this process. All right. Now, this process can also be applied to the rational number. And in that case, the rational number 1 will converge. Okay. So let's look at an example. So an example here, an example for, so do you know, all know that square root of 2 is irrational. So, so square root of 2 is going to be a0, a1, dot, 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 dot. Now let's compute a0. So a0 is going to be square root of 2, integer value of that. That is simply going to be, 1. All right. Now, so your alpha 0 is this guy. Now you want to find out alpha 1. Alpha 1 is 1 upon alpha 0 minus a0. So this is going to be 1 upon square root of 2 minus 1. All right. Now we want to know what is the integer value of this. So although I can use my calculator to compute it, I will use one trick to rationalize it so that the computation becomes easier for me. Multiply top and bottom by square root of 2 plus 1. So if I multiply by square root of 2 plus 1 on top, so let's just write it with a different color pen. So I'm going to multiply by square root of 2 plus 1 divided by square root of 2 plus 1 to the original 1. Now, why am I doing that? Well, we could have used our calculator to do this computation right away at this step, but this will help us out. So let's see, square root of 2 plus 1 divided by, what do we get when you multiply? You get 2 minus 1, which is going to be square root of 2 plus 1. Now, what is the integer value of alpha 1? This is going to be my a1. You will get this is equal to, so what is the integer value of this? So integer value of this is going to be, so square root of 2 is roughly 1.41 and plus 1. So this integer value is going to be 2. All right. And now what is your alpha 2? Alpha 2 is 1 upon alpha 1 minus a1, which is going to be 1 upon alpha 1, which is going to be square root of 2 plus 1 minus a1, which is what? Which is going to be 2. So that is going to look like 1 upon square root of 2 minus 1. Yeah, which looks same as this guy, right? So you can see that the process is going to repeat itself. So if I repeat this process, I will get what? I will get a3 as integer part of alpha 2, again by multiplying by the conjugates here. Let me do one more time, square root of 2 plus 1 upon square root of 2 plus 1, which is going to be square root of 2 plus 1. This is going to be 2. And then I get alpha 3 again as 1 upon square root of what? Square root of 2 plus 1 minus 2, which is going to be 1 upon square root of 2. So you can see that all the AIs is 2 for I greater than equal to 1. Well, it will keep on going forever. So your continued fraction for square root of 2 is going to be 1 comma semicolon 2 2 2 forever. So this is how you would compute the continued fraction for root 2. All right. Now root 3 may be slightly more involving because there you have to do some more computation and there may not be some nice patterns like that. However, there are some special cases for which we can do the computations easily. So note the following. So if I have a number n, which is of form n squared plus 1, where n it belongs to z. Yeah. And without loss of generality, let's take n to be bigger than equal to 2. Because for n equals to, well, we can take n equals to 1 as well. Now, the square root of n, so question, what is continued fraction for square root of n? For square root of n. So in this case, you can see that square root of n, let's call this as x. We want to look at continued fraction for x. So now x is square root of n squared plus 1, right? So we get, squaring both sides, we get x squared equals to n squared plus 1. This gives me x squared minus n squared equals to 1. This gives me x equals x minus n times x plus n equals to 1, or this gives me x equals to 1 upon x plus n, or n plus x rather, and this minus n will come on the other side, will become plus. So n plus 1 upon n plus x. So now this is, you can keep on using this recursively. Let's see how. So I will get x equals to n plus 1 upon n plus, now what is my x? I'll reuse the same thing. I'll get n plus 1 upon n plus x, which is going to be n plus 1 upon 2n plus 1 upon n plus x. Then you go to the next step. So this is going to be n plus 1 upon 2n. And I have already seen what is 1 upon n plus x. 1 upon n plus x can be written as, so this part got replaced by this part here. So it's going to be again, what it's going to be, 1 upon n plus x is going to be, I'm going to write, instead of n plus x, I'm going to write this whole thing. So then we have 2n plus n plus x, right? And keep on going forever like that. You will see that it's going to be n. And then you have 2n, 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 so on. Okay, so this is an example. So for example, if you're asked square root of 5, square root of 5 is going to be, so since 5 is equals to 2 square plus 1, then you have, this is n is basically 2. So you'll get square root of 5 is equal to 2, 4, 4. Right? And there's another short way to write this. So 2, and then you can write 4 bar on top. This bar indicates that it will keep on going forever. So this can keep on going forever. Now note that you have an exercise for square root of 7. This is a homework. So homework, in your assignment, you have what is continued fraction for, question, continued fraction for square root of 7. Now again, note that we have, so first of all, we have an expansion like this, but we always have a naive, quote unquote, naive method in our hand, which is using this computation. The integer parts splitting into non-integer part, and then working with it until you keep on going. Okay. So now there are some special cases in which finding in which finding the continued fraction becomes easier. Okay, and again, by continued fraction, I'm using simple continued fraction. So here we are. So in this case, if your x squared equals to ax plus 1, and your number x, irrational number, for which you are trying to find the continued fraction, is a solution to this expression, x squared equals to ax plus 1, where a is a natural number, right? So first of all, it's easy to see that root of such a polynomial is going to be an irrational number, right? Because you have x squared minus ax minus 1 equals to 0. And then if you look at b square minus 4ac, then you get b square minus 4ac is b square, which is a square, minus 4a, which is 1. Sorry, ac, the ac is the coefficient. So 1 is a coefficient, and then c is minus 1. So you have a square plus 4, right? And that square root of that is basically, if you look at square root of a square plus this guy is going to be a irrational number unless a square plus 4 is a perfect square. Perfect square. So it's a good question to investigate. So question, you should investigate when a square plus 4 is a perfect square. Is a perfect square. Yeah. Okay. Now, why are we investigating that? If a square plus 4 is a perfect square, then you'll have minus b plus or minus b square minus, sorry, b square minus 4ac, which is a solution to this. But in this case, if you use the quadratic formula, the solution is going to be a plus or minus a square plus 4 divided by 2. If this is a rational, if this is a perfect square, then this is going to be rational. And then you will have the whole thing is irrational. That means it will terminate. So you should investigate when is this going to be a perfect square. Now, since you're getting an infinite continued fraction, that should tell you something. Okay, so let's move ahead now. So we have goal now. Goal. You have x squared equals to ax plus 1. Write down continued fraction for x. Now note that we are talking, so this is a quadratic equation, right? So it will have two roots. Here we are talking about x as positive root. Yeah, it can be shown that it's going to be a positive root. So now, so you can write this as x squared equals to ax plus, so now we need to rearrange this. So you get this, so this would mean x equals to a plus 1 upon x. All right, so once you get an expression like this, you can keep on going a plus 1 upon a plus 1 upon. So now instead of x, I'm going to write a plus 1 upon x. Then I'm going to replace that as 1 upon a plus 1 upon a plus 1 upon x. And you keep on doing this forever now. You will see that this is going to be you keep on doing this, so you'll see that this is going to be a, so on. Now you may be tempted to ask the following question: why don't we write this as a, then a and x? Note that this x is not an integer, right? It's not a positive integer. First of all, it's not an integer, so you have to keep on continuing this process. So that's why you get a infinite continued fraction of this form, right? Okay, so that takes care of that. Now, there are few interesting numbers for which the continued fractions are very well known, and 2, 1, 2, 1, 1, 4, 1, 1, 6, and so on, right? So that takes care of the continued fraction. Now you should be able to solve the problems from the assignment. Thank you for your attention.